If I have that copper tube, as I did in the demonstration, and I have a magnet inside that copper tube, and that magnet inside that copper tube is moving, it's moving downwards because of gravity in the demonstration, right? But it could be moving horizontally because I push it horizontal, whatever. Okay, I got a magnet inside a copper tube, it's moving. What happens? Well, my magnet, which is really a magnetic field, we'll call it magnetic field number one. Magnetic field number one, according to that discovery in 1831 by Faraday and Henry, a moving magnetic field relative to a conductor will generate an electric current. We get an electric current in this copper tube. Now, it's a really, really weak electric current. There's no way I'm ever going to feel that electric current. I can hold it and not have to worry about getting shocked or anything, but there's going to be an electric current. Magnetic field number one generates an electric current. Why? Electromagnetic induction. When you got a magnetic field and you got a wire or some kind of conductor and one of them moves, it generates a current. Remember that? We did that yesterday. We reviewed it earlier today. So we've got an electric current here. Now, Oersted in 1819 taught us that an electric current generates a magnetic field. So we've got a magnetic field causing an electric current, but that electric current that was just produced in that copper tube now generates another magnetic field, a second magnetic field. So now I got two of them. I got the magnetic field that was the magnet that I dropped for Ian in the demonstration. That magnetic field generated a current in the copper tube. The current in the copper tube generated a second magnetic field. Now what's important is that these two magnetic fields, they will always act together to oppose motion. Now, opposing doesn't necessarily mean repel. Okay, attraction can also be an opposing force, and I'll give you an example of that in just a couple minutes. The bottom line is there is two magnetic fields, one that I started with, one that was produced by the current that was produced by the original magnetic field that I started with. And those two magnetic fields will act to oppose the motion. So when I drop the magnet for Ian through this copper tube, there's a current produced. There's a second magnetic field. Gravity's pulling that magnet down, but there's an opposing force that pushes it up. So it accelerates at a much, much lower rate than 9.81. Connor, on the other hand, when I dropped the piece of steel that looked the same as the magnet but wasn't a magnet, drop that piece of steel through, you don't have the original magnetic field, you don't get a current produced, you don't get a second magnetic field, you don't get any opposing magnetic force. What happens to it? Accelerates at 9.81 downwards, and you can't beat it then, right? Does that make a little bit of sense? This is what we call Lenz's law. Lenz's law must be the case whenever you move, whenever you've got a magnetic field and a conductor and one of them moves. Whenever you generate that electric current, you will always get that opposing force. If you held a handheld generator and start spinning it around, it actually is a little bit difficult to spin it because there's an opposing force always. You start spinning it clockwise, there's a force that wants it to spin counterclockwise that's opposing your motion. That's a Lenz's law force, a force that acts because the original magnetic field produces a current because it's moving. That current produces a second magnetic field, and the two magnetic fields will always act to oppose each other. Why do they always act to oppose each other? Look, you get two magnetic fields. Why can't they ever attract each other? Has to be opposing force. Otherwise, would violate the law of conservation of energy. I mean, think about that for a second here. If it was ever in a force that wasn't an opposing force, think of the implications of that. You're a weapons designer, and you put a magnet, a magnet inside a copper tube. All you got to do is give it a little tap. If it's a force that helps it along rather than opposing it, what would happen to that piece of that magnet that you put inside there? It would start speeding up, speeding up, speeding up, speeding up as long as the copper tube was. You could you could get it going, thousands or millions of meters per second as long as you had a long enough copper tube. And all you'd have to do to get it going would be give it a little tap. It can't be a force that helps it along. It has to be an opposing force. Otherwise, it would violate the law of conservation of energy. You can't get a magnet going 1,000,000 meters per second by tapping it. You can't get that much kinetic energy by just putting a tiny bit of kinetic energy into it. It violates the law of conservation of energy. So therefore, it has to be an opposing force to take the energy away from it. Jesse? Yep. Uh, yeah, I mean, it would be the force that helped it would be the same as the opposing force, I guess. But it's a little bit tricky because the opposing force is dependent upon the speed of it. So the faster it goes, the bigger the opposing force is. And that's why when I dropped that magnet in that little demonstration, it essentially reached a terminal velocity pretty quickly. It accelerated downward pretty quickly initially, but as it got going faster, the opposing force became bigger and eventually pretty much balanced the gravitational force. So it just kept going down pretty much at a constant speed. Yep. Let me give you a couple more applications. It's going to help you out a little bit with your assignment here, okay? Let's say that we have a block of steel inside a solenoid. Looks like this. Let's make that a light bulb as opposed to a power supply. Which way does the current go right now? There is no current. We got a wire wrapped around a piece of steel. Nothing happens, right? Does the light bulb light up? Nope. Let's bring a magnet, just a permanent magnet nearby it. South pole, north pole. Let's move this magnet this way. Now, it's not inside, but it is approaching it, right? So we do have a magnetic field, and we have a wire, and there's motion relative to each other, right? That's going to generate a current. This magnetic field, the first magnetic field, will generate an electric current. That electric current will be in this wire. That electric current will generate another magnetic field. We'll call it B2. In other words, this thing in here becomes magnetized. But remember, those two magnetic fields, B1 and B2, have to act to oppose the motion. So if this magnet were pushing to the left, what's the pole of this got to be, north or south, in order to oppose the motion? It's got to be south, right? South has to repel south to oppose the motion. If this was north over here, what would happen? It would attract it, and then it wouldn't be opposing anything. It would be helping it along. So we get a north pole and a south pole right here. Now, hold on. The polarity of this becomes north and south, and then you can figure out by the coil rule what the direction of the current would be if you were asked that question, right? What if we switched this up a little bit? What if we said, we're moving this magnet the other way? Now, there's still motion relative to this wire, right? This magnet is moving relative to the wire, so there's going to be a current produced. B1 produces an electric current, and that current in this coil produces a magnetic field B2. What's the polarity of this got to look like this time? We got to have a north pole this time. It's attracting. Didn't I say it was opposing? Yeah. The repulsive force did oppose the motion because it was going towards it. Now, an attractive force opposes the motion because it's going away. So now we would get a magnetic field that was opposite to the way we just had it, and an electric current would also go the opposite way. Does that make sense? That's going to help you with a couple of the questions. I think it's number 1 and number 5, I think, on your assignment that's due on Monday. Listen, if you have trouble with those questions or any other questions, as always, come and see me on Monday. Schedule help for lunchtime, and I'll give you a hand with it.